So we have spent a lot of time trying to solve this problem. That is a hard level minimum window substring. So this was the last one in sliding window. And sliding window is pretty hard. It takes some time to get used to. So I had my solution that was this one. So it works, but it does not give the best runtime. So the idea of my solution is more intuitive. And then I spent a lot of time trying to understand the optimal solution. So I think let's just go over the explanation for the optimal solution instead. We skipped my solution. Okay, but here's what it is if you are interested. Okay. All right, so let's look at the optimal solution here. Let's use, okay, we can only use example 1, I guess. So we have some variables to help us. We have start, final start, which is where the optimal minimum window string will start, the index for that. We have end, and we have count, which is counting the number of letters that we have found in T that we need. So length is gonna be the length of this current window we're looking at. So we start with infinity or integer max value in another language. Letters will be a dictionary. So okay, first we want to put everything in T into this dictionary. So for all the characters in T, if it's not in the dictionary, we this is basically a frequency dictionary. So we set its frequency to be 1. Otherwise, we increment. So this dictionary letters is gonna contain each letter as key and the frequency of that letter as value. Now for the main part of the algorithm, let's have a look. So end is the end of the current window, start is the start of current window. So we are starting end and we're starting with 0 and 0. So we're looking at the first character. Is this in letters? Is this one of the characters that we're looking for? If it is, we increment count, which means we have found one, and we decrement the frequency of this current letter in the dictionary because we no longer need, so we needed 1A, now we no longer need that 1A, we now need 0A. So we still need 1B and 1C. Okay, so for now we have only found 1, so count is 1, length of T is 3. So we haven't found all the letters we need. So this will have to wait. And we have done this part and we increment end to look at the next one. Next one is D. It is not in the letters dictionary, so we don't do anything. And since it's not in the dictionary, it's actually not gonna give us more count. So we just traverse to the next one. Oh, same thing. Traverse to the next. Now we have B. So current window is ADOB. So B is in the letters dictionary. So we need 1B. So we have 1B. So we have now found 2 letters in T that we need. And we decrement the frequency dictionary because we now just need 0b. Still not 3 yet. Continue to increment. Now we have A, D, O, B, E. E is not in there, so increment. Now we have A, B, C. A, D, O, B, E, C. C is in the letters dictionary. We need 1 C. Count is now 3. Good. We decrement, so we have now the letters have still those 3 keys A, B, C, but the values for all of those are not just 0 because we decremented for all of those keys. So now we have count 3 and length T is 3, which means we have found a valid window. So we have this valid window here. End is at C, start is at 0. So the length of this current window is 5 minus 0 plus 1, so that's 6. So length starts out to be infinity because we also need to handle the case where there is simply no valid window. So in that case, we wouldn't have found a single valid window, and that's when length will turn out to be infinity in the end, and that's when we return empty string. So in this case, we have found a valid window. So we update our length to be this current length. And final start, which is where the optimal window will start. Since this window is smaller than the last window, we will also update the final start. Now, the interesting and difficult part. So in this algorithm, this part is not intuitive. So it took a while to understand, but this is also making it efficient. So S start, which is currently looking at A. So the starting character, is that in the dictionary? Yes. Which means we have this current window that is valid. And what are we gonna do next once we find a valid window? Okay. So in my solution, what I was doing is that once we find a valid window, we will continue until we see another letter that is in the dictionary of T. And then we will decide whether we can do something from the left side. So that was my algorithm. So in this case, there's nothing can be done, and then we see another A, and that is when something can be done. So in this case, we have A, B, C. So this is already satisfying the T. So we don't need the A, B here. So I removed A, D, O, B, E from the left-hand side. So that was my intuitive solution, which is not as efficient, but it was more intuitive to me. Whereas in this solution, once we have found this window, we are now looking at the left-hand side and removing them. And so the first thing we do, it is in the dictionary. So we basically remove this because we are now considering shrinking this window from the left-hand side. So we remove that. So earlier, every time we see a letter that is inside the window, we had decremented its frequency because we needed 5, but now we only need 4. But this time, we see this letter that's in T, and before, let's say we had 2 of A that we needed, and now we removed one of them. So now we need So okay, so that's not a good example, but let's say we needed 1a and we had that 1a, and now we remove that a, so now we need 1a again. That's why we are incrementing, because we removed it from our window. So if we needed that a and now it's gone, we need that a again. So we need to increment the frequency, because this dictionary is telling us how many times we still need this letter. So that explains this part. Now, if this letter, if the frequency is bigger than 0, so this is also tricky to explain. So if this letter we were just looking at, we have now removed it from our window, we incremented its frequency, and now we have this smaller window. Do we need that letter? Do we need that letter now? Because if we need that letter, then before we had count 3, because we found 3 that we needed, if we needed that first letter which is now removed, then we now only have 2. So count will decrement because we are now losing one of those letters that we need. So what is not intuitive about this is that you will think, so these letters, the frequency, it's 0, and you just do +1, so wouldn't that always be bigger than 0 then? No, because because we have a case like this. Imagine T is still A, B, C, and S is something like A, B, 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 C. So for the letter B, it is in this dictionary. It is. Which means when we are going over all those B's, it is gonna be in the dictionary, it is gonna come in here. It is only gonna add in one count because we only need that one B. So after the first B, the frequency will become 0. So the count will just increment that time. But all those following B's, they will still continue to decrement frequencies. So it goes from 1 to begin with, and then first B will give us frequency 0, and then all the followings will continue to decrement, so be -1, -2, and so on. So this will actually be a negative number. So here, when we were looking at the left hand side, we increment. So after this increment, it is not necessarily a positive number, because it might have been negative, and it can still be negative. So that explains this part, which I found to be tricky to understand. Now after this, what we have done is we remove the starting character from this valid window. So start is now moved 1 index to the right. So we are gonna do this while this window is still valid. So in this case, it will not be valid after this one round because we removed a letter that we actually need, and then it will go to the next round and we'll go to the next, and this is not one of those letters we need, so it will just continue. Yeah, let's go over this example. It's good because D is in the dictionary. D is not in the dictionary, so continue. Sorry, E is not in the dictionary. Now we have B. So we have B, C, we are still missing A, we have another B here. So when we have another B, it is gonna be in the letters dictionary, but B has frequency 0 because we already found that B we needed. So this count is not gonna do any change. And the letters of B, so the frequency will decrement again, so this is gonna give it -1. Now count is still 2 because we only have B and C here. And the next round we have B, C, B, A. So A is in letters. A has frequency 1 because last time when we removed it, we added it back in its frequency. So now it has frequency 1 again. Count is now 3 from 2. And we have found this one, so we can now decrement its frequency again back to 0. So count is 3, we're going to the while loop. So this length current window is not shorter than the previous window, so nothing will be updated here. So as start is looking at D. Is that in letters? No. So what do? We just move start to the next. So now we're looking at this. Is that in letters? No. Not here. B. We still have count is 3 because we have all the ABC there. So is this window shorter? No. Is this start in the dictionary? Yes. So what do we do here? We increment its frequency because we are gonna remove that. And next step. So how many B's are we looking for? What's the current frequency? Let's see. So we have found 2 B's. We only needed 1. So the frequency of B after that round, after this round, was -1. And now we added back 1, so it's 0. So it will not come in here because we didn't really need that B because we already had another B inside this window. Okay, let's continue. Start E, not needed. C is part of T, so C. Now is this window shorter? No. And is C in letters? Yes. So C had frequency 0 after the last round. So now let's increment that to 1 because we are going to need 1 C again after we remove this C. So after that, the frequency of C is 1, which means if we remove the C, we would have removed one of the letters that we actually needed in the window. So our count is back to 2 again, like this. So after this round, we are left with this window. And count is not 2, so it's no longer in the while loop. So now we continue in, not in T. Count is not 3. And C. Okay, last round. So C is in letters. Now what's the frequency of C? So after last time we removed C, we incremented its frequency back to 1 to indicate that we still need 1C in this window. So count is gonna go up 1, goes from 2 to 3, and frequency of C will decrement to 0. Now count is 3. What do we have? Not a shorter window, so nothing happens here. Now S start, is that in letters? No. So then start plus 1. Next is D. This is still the same length as previous 6th, so it's not gonna go in here. Now S start, is that in letters? No. So next round again. Now this is actually length 5, so that is shorter than the previous length 6. So this time length will be updated to 5 and final start will be updated to this E. And is E in letters? No. So next round again we have B, A, and C. So this has length 4, so it will update length to be 4 and final start will be B. If B is part of the dictionary, then so we increment frequency because we're gonna remove this, so we're gonna need that B. And now what do we have as B's frequency? So B had frequency 0. After this it had frequency 1, and since this was a letter that we needed, now we are counting down from 3 to 2 because we needed this B and now it's gone. So now we lose 1 count. We are back to count 2 and start. Move to the right. So the next window we're looking at is this one. So end is not. So end will go all the way to length of S minus 1. So last round when we were here, we had gone over to the limit of this while loop. So the last round we had final start here, length was 4. So length is not infinity anymore. The final result, this final minimum window substring, has final start B and length 4. So this is index 9. Yes, 9, 10, 11, 12. So 9 plus length 4, that gives us 13, and this is exclusive, so this will actually go from 9 to 12. So this will return that minimum window substring that we are looking for. Okay, so I hope I have explained this solution clearly. Let me know if you have any questions. I will try my best to help. I wonder how long this has taken, if we have time to do some more analysis. Okay, let me see. I have not looked at this follow-up yet. Could you find the algorithm that runs in OM plus n time? So the length of the sum of those two lengths. So what is the time complexity for this algorithm? we are traversing like this. So for each letter in S, since we are using a sliding window, so each letter could be included in this window once, and then the window could move to the right, and each letter could at most be included once and removed from the left once. So that should be a linear time complexity with this whole traversal. And we are also using a dictionary on T. Dictionary has constant lookup, so the time complexity for that would just be, so that's constant, but we do need to put this in the dictionary, so that will be linear in itself. So it will be linear that and linear that, so the time complexity should be the sum of that and that. No other operations that is taking, right, no other. Yes, so that's the time complexity. And what about space? The only thing we're using is this dictionary that has constant space with respect to the length of T. No other things other than constant variables. Just this letters dictionary. Okay, so I think that's it for this problem, which took lots of hours of thinking and looking at solutions. Alright, I will see you in the next one.